Hey everyone, welcome to the podcast. Brian Beeler here, hosting for StorageReview, and we've made the short journey down to Lexington, Kentucky to talk with Valvoline about what's going on in the data center liquid cooling space, and there's a lot going on. And I've been trying to convince George people for years that there's more technology in the Midwest than anyone knows. We're in Cincinnati. I call it the storage hub of the Midwest. I think that's mostly not true, but you guys have a legitimate claim to data center technology down here in Kentucky. Before we get into all of that, you've been here for quite some time, well before data centers were even a thing, but just give us a quick intro on who you are and what you do.
Sure. Thank you, Brian. So I'm George Zhang. So I've joined the Valvoline in 1999 after I got my Ph.D. in chemistry. So when I joined the company, I was studying motor oil, dispersion detergent, formulating motor oil, so 26 years ago. And we actually, over the 26 years, we created the high mileage oil, the segment, Max Life. And we also did the next gen, which is the re-refined base oil to make the motor oil. And also we did the Max Life ATF, quite a bit of the lubricant products over the years.
It's wild. So as we walked in here, we walked past 100 years of automotive engineering, from Model T to now the high-end race cars and a motorbike, and you guys are involved in all of this high-end work around motorsports. It's wild to me to think about, even over all that time, that so much engineering could take place in something, and maybe I've just never thought of it in an elevated sort of way, but motor oil, it's wild, huh?
Yeah. I mean, people don't really think about motor oil. It's afterthought, right? They thought engineering, mechanics, how the parts moving, but when you have moving parts, you have to lubricate. So motor oil actually functions, 4 functions, not just lubrication. Lubrication, number 1, you have to clean, keep the system clean. You have to seal the combustion chamber. That's the viscosity comes into the shape. And finally, heat transfer. You have to cool the engine parts. That's where we have to understand how the heat is being taken away from the combustion chamber to the oil, then to the coolant, then to the air, rejecting to the air. So that's the whole heat transfer loop.
I think I learned about viscosity in motor oil commercials doing sporting events through the 80s as a child growing up. It's a great word, viscosity.
That's right.
So what is it then about what you do with automotive lubricants and heat transfer, and what is it about the entire petroleum industry that's getting into the data center space? How are they similar, or maybe how are they different? I don't know.
So they are more similar than different. So number 1, again, we talked about the heat transfer. We learned so much from the high-end machinery. How do we manage the heat, right? So for the data center, number 1 thing is heat management, the heat rejection. How do you take the heat away? If you talk about, like say, a 1,000-watt GPU, that's really the energy it takes, right? But the majority of the energy is rejected as heat as well after it's done the calculation. So how do we manage that heat? So we understand from the automotive side quite well from the oil to the coolant. So that's transferable, let's say, understanding to the data center cooling. We understand the chemical, physical, rheological, thermal, and we add one more thing, which is the electrical. We never really worry about electrical in automotive, the property of the oil. Now we have to worry about the electrical property of the oil.
Yeah, I mean, it's funny. You've got, I don't know, how many people are in this facility here in Lexington?
Roughly about 700.
Okay, and of those 700, almost all of them know how an engine works, probably.
Yes.
How many of them know how the data center works? Or does it not even matter because you're just dealing with the same fundamental physics issues?
We're just dealing with same fundamental physics issue. But a lot of the people, we all use data center every day, right? You do a search on ChatGPT. That's going back somewhere in the data center to do the calculation, right? I mean, we were shocked to know last year, 2024, all the search on the ChatGPT, the energy consumed is the energy consumed as a country of Ireland in 2024. That's just amazing, right? But again, that energy is consumed, is become heat. You have to manage that heat.
And we're just getting started. Everyone thinks we're so deep into this AI journey. I think on our 90-minute ride down here, we spent 75 minutes talking about the impact on colleges and teaching and coursework and all this stuff. It's so fresh. And if you design a rubric for a college class today, in 6 months it's going to be out the window because we're changing that fast.
That's right.
And it's the demands on the data center are obviously
Sure.
what you're interested in adapting these fluids and your history of engineering into the next step for data centers.
That's right. That's right.
So you said they're very similar. What's new in the data center that's not in the automotive world?
So what's new is really, number one is we have to make sure these are the mission critical equipment. Those are much high value equipment. We have to make sure they're working, they're stable all the time, right? Compared with our automotive world, you do have the time you shut down for quite a bit of time, then you use it again, right? Data center, all the time, constantly running, right? So that's slightly different. But on the other hand, it's less demanding compared with automotive. In the automotive world, you have combustion, which is chemical reaction. You have the mini explosion in the combustion chamber, which create a lot of combustion byproducts, which will get into your oil, maybe even getting into coolant, right? You have to manage that. But in data center, you don't have that. So that's, let's say, a little bit less stressful situation. But one thing that is a little bit different is that you have different materials used for your computer, for the data center, for the servers, compared with automotive.
Sure.
We have to make sure they're compatible. So to us, compatibility is really, really important.
Yeah, the metals are different. The PCBs are different than what you'd have in an engine. Okay.
Think about even labels. The plastic sheets.
The adhesives.
Yes.
Yeah, if you dunk those in, that was one of the first things I learned when we spent some time with immersion cooling is that anything with a label, a few minutes, those labels are all sunk to the bottom.
That's right.
And you talk about the need for cleanliness. I guess you have a little more flexibility in immersion cooling, but when you're doing direct-to-chip with something like PG25 mixed in, the purity of that fluid becomes critical because, as you well know, but for anyone listening, all those heat sinks have little channels that the fluid goes through.
Yes.
And as those gunk up, then the efficacy of your cold plate starts to degrade, and now we've got problems. So we'll get into all of that, but actually, since I already brought it up, tell me about the cooling segments that you're interested in. Obviously, air cooling is the most common in most data centers, fans, giant heat sinks, and even coming off Dell Tech World, we were there a couple weeks ago, they're showing now GPU servers that are 10U, giant heat sinks, still trying to manage sort of the last gasp of air cooling on these very high-end systems until they have to do something else. But direct-to-chip is one where you guys play, and immersion the other, right?
Both. So you mentioned that the heat sinks today, we call the clearance inside, right? The gaps. They are actually smaller than the human hair, which means they're less than probably 70 micrometer. Again, if you have any particles, any let's say even bacteria or the biogrowth, it's going to gunk up the system, right? So it's, like you said, critical to keep the system clean. So when we do the direct-to-chip type of cooling using PG25, we have a patented formulation, which is low solids, which means our formulation inherently has much less solid content. So we have much less chance for the system to gunk up the whole passage of the liquid. And even we have a little bit leak, because those additives we use are liquid-based, so they will be evaporating away. So they're not going to form salt bridge on your electrical components. They're not going to cause any shorting either. Okay.
Yeah, so let's stick with direct-to-chip, because the cold plate is what is very popular now with NVIDIA, showing with NVL72, and people are starting to kind of wrap their heads around it. I mean, liquid cooling direct-to-chip's been around forever. I mean, we have to go all the way back to the 60s, probably, big mainframes that were having it and using it. That kind of went away because efficiencies caught up. But gamers know from closed loops in their systems that are familiar with the concept. This isn't much different at scale. We're still trying to get the heat off of the CPU, GPU. I mean, even now in some of these new systems, SSDs, all the NICs, everything can be liquid cooled, and then we've got to get the heat out somewhere, cool it down, cool the fluid down, and then bring it back in. When you think about your value add there in that ecosystem, what do you do as Valvoline to differentiate? You talked about some of the patents and the design, and I guess you're able to carry that forward from decades and decades of what you've done before.
Yeah.
Sure. But what, for PG25, for instance, how much difference is there in that?
So not all the PG25 are the same, but like I mentioned, right? Our formulation is patented, so that's one. So we do carefully choose the ingredients to formulate the product to have the best thermal transfer efficiency. Again, the base is roughly the same, 75% water, 25% PG. The critical thing is the additive, the corrosion inhibitor, the anti-foam, and also other components we put in to make sure the system stays clean, stays for a long time. And also we from the coolant days, automotive coolant, we understand the testing, we understand the condition monitoring. So we will be working with our customers on the condition monitoring too. So we'll help them understand the fluid property, to monitor any situation that could be happening, right? And one last thing is because we have the worldwide scope of production for the coolant side, so we can produce the PG25 globally. So from supply chain perspective, we are prepared to support any customer which has a global deployment anywhere.
You hit on a couple things that I think IT admins get concerned about when they start looking at bringing in a liquid loop of any kind into the system, even if it's, we've seen plenty of servers that have a closed loop in with a little radiator. That's kind of like the starting point, right? Because you don't need to connect anything. You don't need a CDU. You don't need to the heat rejection system. But as you go upscale, we're immediately concerned about leaks, for one. And when you think about the ecosystem that gets involved in a liquid loop system, I can go by my servers and GPU servers from Dell or HP or whomever, but ultimately there's so many other players in it. There's the hoses, the cold plates, the CDU, the whole ecosystem. There's so much there.
And quick connect, that's actually another critical component, right? You have to make sure you can disconnect, connect quickly, and no leak.
Right.
That's critical too.
Well, you're part of that, but you've got to be integrated with Cool IT and like all these other big vendors, Vertiv and everyone that's out there selling these solutions. The number of partners involved to pull something together like this is really big, and I guess the collaboration becomes more critical than maybe ever for these large scale systems.
Absolutely. These are system perspective, not an individual component. For us, we work with the device manufacturers, the cooling device, and we together will be working with the hyperscaler to make sure the whole system, we talk with each other, right? So we actually heard from like one of the supercomputer system, the server maker versus the coolant provider versus the service provider, they were not talking to each other. They had an issue. They had deposit forming in the system. Nobody knew where it came from, and they were all pointing fingers. So that's a problem when you do not have communication, you do not understand who is responsible for what. So for us, it is critical, like you said, collaboration, communication, understanding the system design, bring the best benefit to enable the system to work the best.
Yeah, well, I mean, you look at a typical data center, and they don't have a water quality guy on the team.
Yeah.
You know, they've got plenty of electricians and HVAC guys and controls guys. They have all that, but they don't have water quality thing. And so when you look at a solution where external water could be involved, there's always the water in Cincinnati could be different than other places. I guess you've got to do things to be more aware there. But when you think about the role of your PG25 in these systems and what the cooling system has to do to get back to IT to say, hey, there may be a service problem here, or there could be a leak somewhere in the system. That's not necessarily your responsibility, but you're part of that ecosystem.
That's right.
And that's one of the things that those guys are most concerned about is how do I identify something before it happens or before it's a problem, I guess. And I don't want my GPUs getting hot to be my first indicator that we need some sort of service or one falls out of the cluster because it overheats, right?
Absolutely. So one thing we are working on, so not only with the cooling device provider or hyperscaler, we're also working with sensor manufacturers. So putting sensors into different places in the cooling loop. So we can find problem, if there's problem, way ahead of time, right? So we measure some critical properties of the fluid for the PG25 side.
Right.
For example, pH, turbidity, right, the conductivity. So we will understand what's happening with the fluid. So as you know, these days the sensor is getting better and better.
Right.
And also the response rate, latency is almost none. So you can real-time monitor the situation, the health of the fluid, without really without being too late. So
Right.
that's the key.
Right.
Yeah.
Yeah, I wonder what, because the cold plates now are, I don't want to call them dumb, but they don't have much technology. They've got hard technology built in, but they don't have sensor technology in most of them. But it would be something that maybe at the connector level or somewhere in there to be able to get that real device-specific kind of information might be interesting at some point as that matures.
Sure.
Yeah, because we think about all these systems like ILO from HPE or iDRAC from Dell. We can monitor every DIMM slot, every drive slot, the CPUs, the heat, the thermal, the fans. We can manage all that. But the liquid loop just injects a whole lot of uncertainty at times into that sort of typical IT motion.
I think for them today, they have the capability for pressure and temperature, right? So, but we can add in, like say, the more parameters to the fluid itself, then we can translate into the whole loop, let's say, situation.
Yeah, it's interesting because as this ecosystem is developing so quickly, and I'm sure you see this as well, there's a pretty wide chasm between organizations that have really nice complete solutions with the CDUs, the cold plates, the heat dispersion units, all of that, and there's others that are not quite so far along in the journey, which I guess for you guys, you've got to be somewhat selective in terms of the right partners to make that work, right?
Absolutely. We want to work with the partner to be able to provide the complete solution, right? Instead of only partial solution.
So in the U.S., I think our split has got to be pretty heavy on cold plate from a liquid cooling perspective.
That is correct.
Do you have a sense on immersion versus cold plate?
We see immersion as more like a longer term deployment. Not currently most of the let's say users are still focusing on the cold plate or direct to chip. The reason is that direct to chip could be retrofitted to the current data center infrastructure, right? If you talk about the whole tank immersion, the whole infrastructure will change quite significantly. So the data center construction will be from ground up. It's for you to retrofit is relatively difficult. But again, the immersion has this advantage.
So let's talk about that. What do you guys see as the key advantages of immersion?
The key, so for direct to chip, no matter what, you still have some component. It is hard for you to cool. So in most direct to chip system today, we still see a little bit air cooling. For the residue part, you cannot use the cold plate to cool, right? So you still combine the liquid with a little bit air. Your PUE still is not as low as you would like to achieve. So for the immersion, you can cool 100%. Right. So I mean, a simple like the number is that the liquid or like a typical fluid is roughly about 1,200 times to 3,500 times better heat conduction than air. So of course, water has better heat transfer, but oil has a little bit less.
Water is harder to dunk your servers into and have them be very happy
so
for long.
That's a range from the 1,300 to 3,500, right? So, but for the oil we are using today for the immersion coolant, it's a little bit lower in the thermal conductivity, but it's extremely low on the electric conductivity. So basically it's dielectric. So you can put the whole system into a liquid. Then you have every part is soaked in the liquid, right? So then heat is transferred to the liquid. Then you have your pump in the back. You can circulate the liquid.
Yeah, that's part of the trick, right? Is that as the TDPs get higher on these components, the fluid can't just sit there or else it just gets hot next to the thing, right?
That's right.
There's got to be movement there. what is the theoretical limit of what you think you can do with immersion in terms of, I don't know how you measure it, watts per rack U or something? How do you think about that?
So what we are seeing is that there's a couple technologies, right? So the most, let's say, the mature technology today is probably the tank immersion. We've seen the tank immersion can go as much as, let's say, the PUE side, 1.03, 1.04. Okay. So which means you're significantly lower than your air, right? Air is roughly 40-50%. You're talking about here 3 to 4% extra energy used for cooling.
Yeah. And I guess we should get to that differentiation that there are kind of some different ways to do immersion. In my mind, every time I say it, I'm thinking of the tank tipped over on its side as Summer or Midas, Doug, whomever, where you're slotting in the servers top in.
Yep.
You talk about power efficiency, though. I was at Addison's data center in DC not long ago, and they're a big supporter of immersion. And one of the things that they said was their failure rates on every single component in the immersion systems go through the floor, almost none. And RAM, storage, CPU, GPUs, all does way better in that design. Okay. And while it's still a little bit scary for another IT admin challenge, because now you're talking about a crane and tables and drips and that kind of thing, the savings and lack of service may be kind of an interesting byproduct of the benefits that immersion can provide.
Yes. So again, we are comparing air versus let's say the immersion fluid, right? So I'm actually having a model here.
Yes.
So hydrocarbon. So we use hydrocarbon as a cooling fluid. It's only carbon with hydrogen, right? Nothing else. So when you have hetero atoms on this molecule, then you will create a problem. For example, if you have fluorine or chlorine, that's forever chemical, right? We are only using the single phase immersion, which is hydrocarbon.
Right.
So they are very, very, let's say, pure chemical. They are very inert. They're not going to react with anything. Same as air. You put your system in the air, it's similar as you put your system in an immersion fluid.
Yeah, we've seen some creative immersion solutions. Hypertech is one that's really designing servers for immersion, which I think is interesting. Yeah. And then there's a bunch of guys that just sort of retrofit a Dell or HP or Supermicro or whatever and dunk them in, which can be fine. But I think what the industry learned very quickly, and I'm sure you guys saw this in the labs, is that cables designed for air servers don't last long in oils and stickers and glue and things that are on drive labels or DRAM labels will fall off and foul up your oil cycling system in those tanks. What were some of those early learnings like for you guys?
Yeah, for us, again, you're absolutely right. So the compatibility is really the first thing we have to do, right? So if you have a system that want to implement the immersion cooling, we will ask what kind of material you use, what kind of system you're using, right? The metal, the plastic, the elastomer, the thermal interface material. If they have a thermal glue, we want to understand what glue they're using. We've seen like some of the cable, the color or pigment can be picked away by the fluid.
Right.
The fluid will change color.
Right.
So even we all know, like I say, the color will not. It's not an indication of performance. But to the end user, that's everything.
It looks,
right?
it
looks bad.
foul. Yeah.
So we have to understand that. We have to work with the system or the hyperscaler to make sure we have the compatibility problem or the compatibility resolved at the beginning before we go into really implement the liquid.
By the way, I don't think the mics picked it up, but I'm pretty sure that was a V8 I just heard, which really lets you know you're at Valvoline when you hear a nice V8 fire up in the background. But staying focused on the data center for a little while longer. So it's not, I guess it's not really your job to qualify cables, but you end up there anyway in a certain way, don't you?
That's right. So one of the we recently just did one of the study is wicking. So you want to make sure your liquid is is not wicking in between the line, the copper with the casing, right?
Right.
So those are really critical for us to understand what kind of let's say manufacturer are producing the best cable we can recommend to a customer. That's probably you can use. And some of the PVC or some of the type of plastic for the cover could become really brittle, right? So we will suggest use polyurethane if possible, things like that.
We've got to be at the point now as an industry where that's pretty widely available, though,
right?
It is. A liquid immersion certified cable.
Yes, we have 2 organizations we are very actively involved. One is OCP, Open Compute Project. So we are in there like some weekly calls. We get together with them. We understand the material list, right? That's one. That's mostly both the immersion and the PG25. Then there's another organization called ASHRAE. So ASHRAE is a little bit more on the PG25 side because it's the HVAC route, right? ASHRAE also has a wetted material list as well. So the list getting longer and longer. But again, those are giving the customer or the user a guideline of what materials you should be careful, what materials you should be testing with before you implement the liquid cooling.
The other question we get all the time is about networking and the light transfer for some of the high-speed fabrics through the oil. If the lubricant gets involved in there, does it manipulate or deflect light or do something? And I know you've worked through that.
Yes.
What's your feeling on that concern?
So today, a lot of the let's say the hardware manufacturers solve that problem by moving the switch out of the liquid, right? So on top of the liquid, so that's actually bypass the problem. But for most of the system we are seeing today, the switch or the connection, the fluid we're using, we have not seen much of the problem. We heard there's some we call signal integrity issue, right? But so far, our study showed we have not the fluid has not caused that problem. But if there's something we could manipulate, we could manipulate the dielectric property or dielectric constant of the fluid to mitigate that problem. We do have that, let's say, tools in our tool bags.
So you talked about OCP, and I think that's an interesting one. I think you guys were there last year in October. I think I remember seeing the booth. It's got to be weird for people that don't know you when they walk into this little expo in San Jose Convention Center. See Valvoline, what the hell are those guys doing there? If they're not used to administering that kind of thing, because OCP talks to a wide group of people.
Sure.
I don't know if you were there, but what's the feedback you get from that audience?
Again, like the number one, like you said, people think, oh, you guys are car guys. Why are you in the computer show, right? But to us is again, we try to reiterate what we have learned in 150 years from the lubricant, from the coolant side. We take that learning to a high-performance computer, and we try to educate people. Heat transfer is heat transfer. Material compatibility is chemistry, right? We have both. We understand both. We can put that both into use.
Right.
So again, we are, let's say, relatively new into this industry. We have a lot to learn, but we are learning and we are progressing.
OCP, I think, has 2 different working groups, or whatever they call them. I believe they've got a liquid cooling immersion and a liquid cooling directed chip.
That's
two separate working groups, right?
Yes.
So they're getting really serious. I mean, Meta's put a lot out into OCP about what they've done.
Intel as well, right? NVIDIA, Microsoft. Again, these are impacting the performance of their hardware in the future, right?
Well, NVIDIA, really, right? Because they're driving TDPs through the roof with their GPUs and whatever comes next. I mean, it's only going to get more intense.
Yes.
We've talked a lot about the direct-to-chip and then also immersion, but you work with some partners at Data Center World a couple, I guess, 2 or 3 months ago now in DC. You were there with iZotope. I know you've been a partner of theirs for some time. They do it a little bit different.
That's right.
And unfortunately, I think most of their servers have metal lids on them, but the display unit with the acrylic lid on, you can really see in there with the lights.
Yes.
But talk about what they're doing. I know it's not your product, but you're familiar with it.
Yeah. Again, so when we talk about tank-style immersion, you put quite a bit of fluid, right? Typically 200, 300 gallons per tank.
Okay.
You dunk the whole server, like say, vertically coming into the liquid. But for iZotope, precision immersion, so the idea is kind of taking the direct-to-chip approach, but you have a little bit less fluid, right, per rack. Then you pump the fluid to the top, and you spray the fluid onto the hard components.
Yeah.
Typically GPU, CPU,
Sure.
SSD, the DRAM, things like that, right? Then the fluid comes down to the bottom of the chassis, we call chassis, then get pumped back again slowly. So the pump is a very small, let's say, power consumption.
Right.
Again, for using these precision immersion, I guess one advantage is that you don't use. To us it may not be an advantage, but to the user,
fluid.
yeah, you less fluid. But on the other hand, it's because it's horizontal. So retrofitting becomes a possibility.
Well, and it's more comfortable because you're now back into a standard
That's right.
rack system,
Yes,
right?
yes.
And then you're rigging up in the back
Yes.
to move that fluid. Yeah, it's interesting. I know they've been showing that at with HPE systems for some time,
Yep.
and they had a couple new things that were pretty cool. So yeah, I think that one's a fun one to explore. I think we'll see maybe some of that in the lab tour later today. All right.
Exactly. And also there are a little bit newer design these days. Is more active spraying.
Right.
You probably have seen that, right? Those more like not sitting. The surface not sitting horizontal or vertical. It's with an angle. When your fluid comes in, spray from the top, then the fluid is touching everything, go to the bottom.
Well,
right?
that's the kind of the neat thing about their design is, it cascades over the entire
yes.
motherboard.
Yes.
And you're going to pick up coverage for all those little capacitors and transistors and
Yes.
your out-of-band management and your NICs and all that stuff is going to benefit from that cooling.
That's right.
The things that aren't even that hot, but they still wear.
That's right.
And we've seen some of these servers. We've lost motherboards not because the CPU socket died. It's because some 49-cent part blows up on it and there's not
much you can do.
No, you don't have a solder kit normally
That's
at the data center to go in there and fix it. I mean, Kevin probably does, but most people
they don't solder anymore.
They don't teach that. I don't think in server admin. We didn't talk about it. You hinted briefly at it earlier in the conversation, but multi-phase cooling. What's your take on that?
So multi-phase cooling has the advantage of the heat of the evaporation of your liquid going from the liquid phase to the vapor phase, right? It takes up more heat away from your components. But the biggest problem is that right now, almost 100% of the molecule used for the two-phase or multi-phase cooling is a forever chemical, the PFAS, right? So the PFAS so far, as an industry, as a whole society, we have not found a way of managing it without causing long-term environmental problem.
Right.
So for that reason, we studied, even like say it has efficiency benefit, but it's detrimental to the environment. So we decided not to pursue that.
Yeah, it sure looks neat when it bubbles.
Yes.
But I guess that's not a good enough reason. You highlighted the thermal properties. I went for the visual.
Yes. But I think that when you say bubbles, there's a second, let's say, the complication for that is that you have to have a CO system.
Right. Escape of the gas is problematic, right?
Even more problematic,
Yeah. So for full immersion or tank immersion, if we look at this in 10 years, how different will that fluid be than what you have today?
We've seen the fluids getting, let's say, again, we look at 4 major properties of a fluid when we design the system, right? Again, we talk about viscosity. That's number 1, because you want the fluid to be low viscosity so it can flow easily.
You got to move it. Right?
Number 2 is thermal conductivity. Number 3 is heat capacity. Those 2 are linked together, but they're not same property. Thermal conductivity is how you take the heat away. Heat capacity, how you're holding the heat, right? They are linked. Number 4 is the density. So the dense the fluid, the better. So the 4 properties you put together, there's not a lot for us to manipulate if it's hydrocarbon.
Right.
So we are still working on make it, let's say, more purified, better on these properties, a little bit dense, a little bit low viscosity. But you can imagine when the viscosity gets so low, it becomes flammable, right?
That's problematic also.
Yes. So,
and I think Europe or some other areas have some more stringent requirements on.
More Asia, yeah.
Asia. Okay,
yes.
right. Have more stringent requirements.
We look at the flash point.
Right.
So 150 C is the North America requirement above. And in the Asian countries, it's a 200 or 250 C.
Oh, much higher.
Much higher.
Wow.
But then when it gets much higher, the problem is that you have to use much viscous fluid, right?
You lose
then
that
you lose
advantage,
pumping power,
yeah.
yes.
Huh. So still oil-based. Can you put additives into the oil to help any of those four challenges?
Yes, you can. But then you have to be very, very careful. Number one thing you don't want to break is the dielectric property, right? The non-conductive property.
Yeah, I guess if I'm going to dunk a couple $1 million of GPUs in some oil, I'd like it to not destroy my equipment.
That's right. So you can put, there are quite a bit of additive we can use, but to manipulate these four properties is quite difficult without causing other properties to go through the roof.
Out of balance,
yes.
right?
Yeah, out of balance,
okay.
yes.
So then for the closed loop business with the PG25, what does that look like going forward? Can that be further enhanced, the fluid itself?
Yes, before you go to PG, let me actually go back to this. So a couple of things we can do for the immersion side. Number one is how do we make the hydrocarbon with less carbon footprint? We do have ways of doing that. That's one. And secondly, can we use bio-derived? So for bio-derived, the problem is that we have all single bond. For bio-derived, you have some double bond. The double bonds are the problematic part. They're reactive. So how do we create bio-derived hydrocarbon, but with all saturated single bond? Then also the cost is acceptable, right? We do have ways of doing research. I think in the future we may be able to go that route. Okay, so that's on the immersion side.
Right.
If you look at the PG25 side, similar. So the PG today most is from petroleum process, more like a byproduct process. You take the propylene oxide, you make the propylene glycol, but there are also wood chip based and plant-based PG as well. But again, the cost is right now is really, really high. You buy the environmental benefit, right? So can we have the process better, or can we make the volume better so eventually the cost is comparable? Those are the things we are researching into the future too.
I'm regretting getting a C- in high school chemistry right now.
Chemistry is the key.
So who would have thought that for aspiring IT professionals that a chemistry background would be useful?
It is useful.
Thankfully, it's too late for me. I'll just rely on smart guys like you to help.
We can work together.
Okay, we'll collaborate.
Yeah, we'll collaborate. Yeah.
You do the nerdy stuff, and I'll run the social media. We'll figure that out. That'll be no problem. So speaking of that, we're going to go after this. We're going to wrap up. We're going to go to your data center labs. Yes. Tell me what's in there. What are we going to see when we get in there?
So here in Lexington, Kentucky, so we have the lab. We do the compatibility testing, like I mentioned. That's the number one thing, right? And because this is a working lubricant lab, we do a lot of the oil formulation. You will see that. I can explain a little bit to you, but that's not the data center related. But we do have immersion rack over there. You will see that.
Great.
And also we will have some of the thermal and electrical measurement device in the lab too.
Cool.
And finally, I may show you guys some of my proud part of the research is tribology, which is not too much linked with the IT side, but again, it is how the lubrication friction wear comes into play, right? So that's where the lab we house the study of the rheology, the thermal, the electrical properties.
Okay.
And beyond that, we have a lab in Ashland, Kentucky, where you mentioned the closed loop cooling system. We actually set up a closed loop cooling system there without CDU, just pump the fluid around, change the radiator or the heat exchanger, right, from copper to the aluminum to see the efficiency.
Okay.
And the same fluid we develop over here, we test over there, then we see any benefit, we'll come back, reformulate, and test over there again.
So you're really doing a lot of your own testing too, not just relying on partners to do that work for you.
We do quite a bit of our own testing.
Okay.
Yeah.
Well, cool. Well, we'll go check that out next. If you want more information on Valvoline and what they're doing in the data center, we'll put a link in the description for that. And George, I mean, this is awesome conversation. I appreciate your time.
Thank you very much.
Thanks for having us down here.
Thank you.